here. You're welcome to my class. This is Embedded Systems, Real-Time Embedded Systems. The module code EEE8087. I'm very pleased to see you in the class. Usually we begin lectures at 5 minutes past the appointed time, just to let the late arrivals. So it's another probably a couple of minutes, maybe a minute and a half. So let's wait for this. Meanwhile, I'll have a look at the class. So at the moment, Zoom shows that I have 30 participants, and 2 of them it's I, so I have 28 students. Not bad. The class altogether, however, it's larger, isn't it? Just let me check how many do we have in the class in general. EEE8087. NES shows that we're supposed to be having 46 students, so probably a couple will be arriving soon. Well, but anyway, it's 5 minutes past 11, so we need to start. So hello again, and we are starting our module, which is 8087. First things first, I need to share my screen. And there it is. So this is our Canvas page. This is what you see when you log in into Canvas and open this module. It contains the names of the lecturers whom you will see. You know me, it's Alex Bystrov. We did some modules before. And there will be another member of staff, Dr. Fei Xia. He is our senior researcher and lecturer. He is actively involved in the research on the topics he is going to talk about. It will be the second half of lecture material. So this is to say that our lecture material is split between mine and his. So the first week, this week, we'll be going through my lectures, and the next week it will be Fei Xia lectures, right? Now, from this page, we can travel into the specific pages where the actual PDF files and lecture recordings sit. So, module materials. So you can click this or just modules here. It's the same link. So here we will see our lectures. Right, so this is the link you will need for the next couple of weeks. This is what we are studying within the next, this and the next week. And after that, it will be followed with 2 weeks of coursework where we will be developing things by using development boards, ARM processors, and you will be working individually, and how you access the hardware and so on. And the specification of the coursework, it will be discussed later. So at the moment, we need to go into the lectures. Right. This is my plan for the week number 1. So it's I, and this is our first week. Right. So in the week number 1, we are going to go through this material from here to, yeah, these are my lecture notes and pre-recorded lectures. This is slides, talk, slides, talk, slides, talk, slides, talk. And obviously it's quite boring to watch somebody else talking without actually communicating to the person. So every day we'll be having our interactive sessions. So the first is now. I decided to have it in the morning because it is before you start studying. And every other day, so it will be Tuesday, Wednesday, Thursday, Friday, we'll be meeting at 4 p.m. after you have finished the busy day of studying. And then we will be discussing the appropriate topics. Right? So altogether for 5 days of the week, we have 1, 2, 3, and 4 topics. Out of these 4 topics, probably this one is a kind of longer than the others, longer because it has more bullet points and more talks there, right? So probably it will take slightly longer, therefore this is what we are going to be discussing after a day and a half of your hard work. It will be tomorrow evening. So by tomorrow evening, I'm expecting you to go through this material. If you do not finish it, it's fine. So tomorrow evening, it's okay. So we can deal with a part of this. But in general, try to finish this by tomorrow evening. So half of that today and half of that tomorrow. Altogether, the plan is here as the first bullet point. That's the plan, right? The plan is to have 4 weeks of study, and within these 4 weeks, weeks 1 and 2 are lectures, and also questions and discussions, interactive sessions after each lecture. Well, by the way, normally lectures are formal lectures. I mean, normally before the coronavirus madness, they were just formal lectures, which meant 2 hours of lecturing, me being in the class. And as the class, as you see, 40 students or something about this, then it's quite difficult during the lecture to have a detailed interactive discussion. So I was staying after the lecture usually for 15 minutes, sometimes half an hour answering questions. So these days it is more structured. So we are live during the lecture. You see my recording. Right. But altogether, the number of hours contact hours is significant. So this is the theory material. Then there will be a set of presentation topics distributed to you and will be distributed at some point earlier the next week. And at the end of the week 3, there will be presentations taking place. Right, it is the first item of our assessment. I will show you where the assessment happens. So it's assignments, it's here. Everyone will have a chance to talk. All right. So it's a conference or workshop style learning. It is a valuable addition. It's quite different from what traditionally we have in the undergraduate courses. So it will be study of advanced topic, usually by book or by papers, and then presenting your understanding and the discussion of that. The presentations are not very long because there are 2 academics on the list, and we need to examine plenty of students within a couple of days. So don't be worried. So it's not half a day of presentation by each of you. It is a limited number of minutes and limited number of minutes per question. So it's reasonably safe for you, but usually students respond quite well to this opportunity to talk. Well, the second half of the course, weeks number 3, altogether are 4 weeks. So weeks number 3 and 4, it's still just before Christmas. We will have laboratory coursework. It is online, but the laboratory equipment, it's physical, it sits in the lab. So you will be able to see the equipment with cameras, program it remotely, observe the response on video, on the camera and so on. We will have certain meetings and sessions in the lab during that period. So we'll be seeing physically each other. So I'll be walking between the workstations and trying to identify your issues and needs and supporting you, just initiating this kind of support. And there will be also plenty of online sessions in support of your work. So for those online sessions, you will have to develop a skill of asking questions. Right. I already had this experience before, and we just finished the course on, it was microelectronics coursework with Cadence software. And what I found that, well, actually, I found it in the previous year, it was confirmed just yet another time, that it is significantly more efficient to see each other in the class, in the lab, rather than online. So we need to combine these modes of study, personal meetings and online meetings, in the most efficient way. So I'll show you how to do it while in the class, and then you'll continue with online work. The support will be provided obviously online as well. The assessment of the whole module will be happening by, well, there are 2 items of the assessment. The first one, let's go into assignments on this module. Says assignments. I have more than you have, so it's kind of template for something else. Ignore that. So these are our main assignments. This is the coursework report, which you need to submit. It's the main aspect of assignment. It's, I think it's 60% of the overall mark. It will have to be submitted online through Canvas, and the deadline for this will be after the holidays. It will be 10th of January. It's the first exam week. I know that you don't have many exams in the semester, so it is okay to occupy the first day of the exam week. And of course, those who have exemptions due to all sorts of tax, the deadline can be extended a bit. So the module finishes just before Christmas holidays, and then after the Christmas holidays, you are submitting the reports. The module is designed in such a way that it is potentially possible to finalize, to write the report during the scope of those 4 weeks. However, I know that usually it does not happen. Students prefer to submit their reports slightly later, after they had a chance to sit quietly and think and discuss the content of the report. Right. Otherwise, it will be just a set of brief notes. So this is why I'm setting up the deadline not on the last day of the module, but rather after the holidays. The other aspect is this presentation. The deadline is 9th of December. Why is it 9th of December? It's Thursday. Let me check. Yes, 9th of December is Thursday, because the presentations will be happening on 9th and 10th, right? But I would like you to submit your presentation slides at some point, right? So the presentation slides should be submitted on this date, 9th December, right? Well, why I need those presentation slides? It's because all our marks are double and triple checked by the external examiners. I would like to have some evidence of the class making those presentations. So I would like to have the copies of your presentations in PDF format uploaded to Canvas. The mark is given not on the basis of those presentation slides, but rather on the basis of your talk and answering questions. But sort of the slides provide a partial evidence of your achievement. So these are 2 items on the list for the assessment. The deadlines are here. Any questions about this? Because the next for me will be to open my own presentation and just go quickly through that. Do you have any questions about the deadlines, the structure? No. Good. Do you have my timetable in your applications or in your calendar? The timetable, which includes the session, which is now, and starting tomorrow and until the end of the week, it starts at 4 p.m., our online sessions. Do you have this?
Yes, we do.
All right, so thank you very much. So I was hoping that someone will switch on the microphone and shout. Great, so I hugely appreciate this interaction. The thing is that it's quite difficult to talk sometimes when there is no feedback coming back. And now I see that you're first of all listening, and now I'm sure that you will not become lost, and I will keep seeing you throughout this first week. Thank you. Right, so, I just looked at the number of participants. Now we have 39, so it went up, which is great. I usually begin this module with a set of slides, and this set of slides does not belong to the assessed material, so it is an introduction to the module. It includes the title, it includes the names of the academic staff, it includes the name of the school, aims and objectives as usual. So what we are going to try and what we are going to achieve in this module is hardware, software design, modeling of embedded computing systems. Modeling will be on the software side, and my set of lectures will be concurrent theory of concurrency and concurrent programming. It will be a modeling of the processor and power management on the side of fascia. So expect interesting things here. Protocols, design, concepts, and scheduling. Scheduling, it's one of the large things for both parts of the course. So in my part, it will be present, and fascia will be talking about scheduling in terms of efficiency of computation and power management. So it will be quite interesting. Also, please download the book by Butazzo in PDF format. This book is available electronically, and the link is on Canvas. Please do it earlier rather than later. And this book will be massively used in our presentations, right? So many topics will be taken actually from that book. Now, design concepts, it's the solutions where we are arriving to. And protocols, it's more related to models which just begin their journey towards the implementation. So we depart from models and then develop protocols. What are protocols? Protocols are orders. It's in which order you perform switching of signals, for example, or actions in software design in programs. Protocol is the order of things. Design concepts, of course, it's a philosophical idea of describing a design at a very high abstraction level. Right? For example, you will have a concept of concurrency, concurrent programming. What is that, and how is it different from sequential programming? What does it involve? So you'll see that there will be, for example, critical sections, mutexes involved. And in order to understand them, we need both models and examples with programs. So we'll be trying programs and see how models work. There will be, for example, a model, a concept of ACM. Right. Is there anybody swimming at the moment? So that's the noise which is consistent with someone either swimming or digging or running through the bushes. What's that? Okay, so it comes down. Well,
两个自由选择。他给你回答问题了。有啊，他给你回答问题了。对，没答一个。
It was Yuchen Shu, right? Hello, Yuchen. So, well, I hugely appreciate when people interact and switch on the microphone and shout questions, but please, if you need to go through your papers and the papers are sitting on top of the microphone, probably it makes sense to mute the microphone for a moment. Okay, no problem. And finally, we do this design of a system, and will be an implementation of a simple scheduler. It happens just before Christmas, and the application eventually operates the LEDs on the board, and they will be flashing like Christmas lights. So it will be consistent with our expectations to the holidays. Right. The idea is that the rationale, the idea that in the formal lectures we cover a set of hardware and software aspects. They're both theory at a high level, which are concepts, and they design solutions for that, such as details of software implementation. So what we'll cover, it will be real-time aspect, it will be Petri net models, concurrency concept, arbitration. It is a solution for some particular things within a concurrency concept. There will be communication modeling, asynchronous communication mechanisms, and there will be embedded design, threads, processes, scheduling, programming, setting up communication links between processes. So if you execute several programs at the same time, it makes sense to somehow make them work together. ACM and architectures will be studied with Dr. Shah, and why it is so, because actually it was his PhD dissertation ages ago about asynchronous communication mechanisms. So what are those ACMs? Well, it's a very interesting thing. It's how to make processes in a complex system work together even in the case that one process, for example, freezes and stops supplying the data. Right? So you don't really want the other process and the other and the other and all of them eventually start waiting for each other. So with ACM, such decoupling between processes is possible, and as a result, the system can maintain high performance. So it's all about this. It's all about designing buffers in a particular way. And this may also introduce certain errors in the functionality, and one needs to be aware of that and build a system around those errors. So I didn't stall eventually. And practicals develop skills and help to understand deeper the theory. So we'll have software design, scheduler, real time, of course. We'll use ARM platform, which is nice. Deadline, please ignore this. It's not Friday, it's actually, instead of last Friday of the semester, it is now the first Monday of the examination period. It's on Canvas. Please ignore this statement. Right, and from now on, I start talking about the technical introduction into the general field. From here, from now on, it will be just a few slides, the general concepts, and after which I will finish our talk and leave you until tomorrow. So the subject of our study is an embedded system. What is an embedded system? And people try to define it. Well, what people? Academics mostly, because engineers, they do not define things. Instead of that, they just build them. So traditionally, it just happened that computers appeared, and then engineers found applications for computers which are not just computing, but using a computer as a component of a system, right? And they just kept doing this, and it eventually became an embedded system. But as for academics, they tried to define it. 2002 attempt, Wahid and Gevarkis. Why I'm putting those names? Because these are the authors of a book which is frequently used as an introduction to embedded systems. So they try to define it as nearly any computing unit not used as a desktop computer. Right, but what about laptops, servers, mainframes? They're also computers. They also can do just the basic computation and produce results in a table. So why is the desktop computer? What if the desktop computer is used to control something throughout the network, or just for Skype or any kind of chat? Right? So it becomes a communication component rather than a computer. It's not computing numbers and putting them in the table. So it does not fit this definition. So desktop potentially may become an embedded system according to this definition, although it contradicts this desktop there. And laptops, servers, and mainframes can be used for non-embedded applications, although they are not listed here because only the desktop is listed. So not a good definition. A better definition was given by Gupta in 2002. Again, it is yet another book which is used for introduction. So he put this as several points, 3 points. An embedded system employs a combination of hardware and software to perform a specific function. Yes, it is a characteristic. It's not a definition, but characteristic. A combination of hardware and software to perform a specific function. So in the past, the blocks were just hardware. Now we can use software as a component of the system. It's quite interesting. Furthermore, it opens an opportunity of partitioning the system into hardware and software, and you can balance hardware versus software. You'll see later that they have different characteristics, so optimization is possible within this domain. Embedded system is a part of a larger system that may not be a computer. So yeah, it's a good point. So, using a computer or embedded system as a component, which may or may not be. So it's kind of an overclass. It's an overset over a set of just computers for producing tables of results. So it may or may not be a computer. So it's a broader spectrum of application. Good. And the last point is extremely nice and relevant to our module. An embedded system works in a reactive and time-constrained environment. Reactive means that it responds to the inputs. So we need to study models and protocols for communication between processes. So the request comes and somehow the embedded system or a program in the embedded system should respond to this. That's the whole point. It's reactive. And this response should happen in a timely manner. So we are getting those real-time requirements. So we need to respond before the deadline. So it's real-time. So time-constrained environment. So it is a very, very good definition. It includes a combination of protocols, real-time, and says that an embedded system is a component, and internally it uses hardware and software, and it's possible to do optimization by moving things or elements of functionality between hardware and software. So excellent definition. So let's keep it like this. There was a book by Williams, quite old one, 2006, and he went through a variety of properties and just pinpointed a few and put them in the list. And this is a list which is useful for the beginning of the thinking process, how we think about embedded systems. General characteristics. Usually an embedded system has a latency limit. Right? So latency limit means that there are two characteristics of performance of any system. One of them is latency, the other is throughput. Latency means that when an input arrives, then at some point you expect the response to this. Right? And the time between the request and response, it's the latency, it's the lag of the system. And throughput is how many data items per second or per unit of time the system is processing. So here we are talking about the response time. Why response time? Response time is crucial for protocols. It's all about what we were talking about before, reactive and time-constrained environment. So latency limit they have. It's the real-time aspect. We have event and time-driven scheduling, right? Scheduling. What's the scheduling? The keyword here is scheduling. Scheduling, it's about starting, stopping, pausing, and restarting again different processes in the system. Well, a process is an instance of an executed program, and sometimes they're called tasks. Why tasks? Because different word. Well, you can use them interchangeably, of course, but a task is a broader idea. So task can be implemented as a process or a thread. Right? So a thread is a function which is executed and can be started and stopped, and a process is a program which is executed, can be started and stopped. And a task, it's a software construct which can be started and stopped and executed and controlled somehow. So it's easier to talk about tasks sometimes. Now, this control can be driven by events or by the time. Events, it's those interactions with the environment. So there is a wire connected to some sort of a sensor. The sensor registers the data and gives the pulse, and suddenly the computer wakes up and processes the data. So it's event-driven scheduling. And time-driven, it's virtually the same with the difference that the wire is not connected to the outside sensor, but it's connected to the internal timer. And based on this timer, the system wakes up, usually periodically every millisecond, for example, and it does the job. Well, it could be once a second, or whatever it is. So time-driven or event-driven. So the difference is event-driven, it's external inputs. Here you have internal. Low-level programming is a very frequently exercised feature. Why? Because every time you create a new system with new hardware, you need to go low-level in programming because you have registers, you have specific to hardware protocols. In our coursework, we will have a bit of low-level programming, but we will be doing it in C language. So sometimes it is possible, and I'm trying to make life easier with this. Software tightly coupled to special purpose hardware. This is, remember I mentioned this before, employs a combination of hardware and software. In particular, said that here we can optimize by moving functionality between hardware and software. Here we have software tightly coupled to special hardware. So you write programs which serve particular hardware, and sometimes you also bring new hardware in your system if your software is not fast enough. So sometimes you may want to serve a large screen by using a hardware accelerator, graphics accelerator. Those who played games, they know how important it is. So frequently it is done. Dedicated specialized functions, of course, based on the above reason. Computer inside the control loop. This is as we are including the system as a component into a larger system. We can use the computer as, we should use the computer inside some sort of a protocol, and the protocol goes forever. So you power up the system and the airplane or car move, right? And they keep moving for a long time. So multiple cycles of operation, it's control loop. The computer is a component within that. Multitasking, yeah, it's an important point, a very important. Why? Because you have just one computer. It's quite expensive, actually, in a sense. Not just money, but it's a large chunky piece of metal. And very often you may want to execute multiple tasks. You may have, well, in the same car, you have different subsystems, and each of them require a separate task to be controlled. So instead of putting thousands of computers into the car, you limit yourself with, say, a few dozens, and each of them can execute multiple tasks. How it is done, the processor quickly switches between one and the other, and the overall impression is that several tasks are executed at the same time, even if the processor has just a single core. But if it has multiple cores, then it's easier. And those tasks, this kind of fast switching between the tasks, it's the business of schedulers which do scheduling. So everything is connected with this. Continuous running. So as a computer sits inside a control loop, this control loop is running continuously for a prolonged period of time. So it's not just a one-off computation usually. There exist also very specific metrics, such as safety critical applications. So what is that? So if there is an error or a fault, the system should be able to recover, execute the task anyway, even if there is a fault. So it's fault tolerance. It could be execute the task with limited accuracy or limited performance. It's gradual degradation of the quality. It's graceful degradation principle. So for safety critical applications, we have a variety of specific metrics. And metrics there are reliability, availability, and so on. Security, as you have, for example, your mobile phone or computer, you have HTTPS everywhere, secure protocols, you have a credit card, bank card, so security is implemented there. Security is very important. Power constraints. Well, power, it's one aspect of power supply design, by the way. It can be power constraints or energy constraints. Power constraints is mostly about energy per unit of time. It's about how hot the processor is running. So sometimes it overheats and breaks down. Energy constraints, it's for how long the processor can run on a single battery or on a single charge of the battery. So it's more relevant metric for modern variety of modern systems. Variability tolerant designs. We have more than half of the class from microelectronics background. You know that when you design modern chips, there is variability there. So the delay in different gates and different blocks is different, and sometimes the system may stop functioning because of that. So they need to design the system in such a way that it still functions under this increased variability. And variability is caused by small feature size that everything becomes deep submicron. How to achieve it? Well, there are different methods for that. One of them is to slow everything down. The other is to slow everything down in case of increased variability, but in a clever way. For example, it's possible to sense the minimum voltage under which the system still operates correctly. And as soon as it starts increasing the rate of errors, you can boost up voltage slightly or reduce the clock, for example. So it's so-called razor technology in ARM. Very interesting stuff, by the way. Now, software, hardware, co-design. I already mentioned this. Where? Yeah. Hardware plus software, right? And the same function can be implemented in different ways. So, for example, you can display the image on the screen by using a graphics accelerator or just outputting the data pixel by pixel into the frame buffer. So what is better? Well, you know that with the hardware accelerators, everything becomes fast, of course. But software also has its nice features. Software provides features and flexibility. So it's very difficult to create a piece of hardware which is hugely customizable, which has tables of data, lists of things, and so on. So hardware is usually silly and stupid and fast. Right? So software is better for creating large arrays of data and make it flexible by changing the data recorded in the memory. Features can be easily added into the software by upgrading the software, adding a new plugin, for example, uploading an image and changing the background in the mobile phone, something like that. So software provides features and flexibility. On the other hand, hardware, such as processors and so on, its performance, fault tolerance, security, energy power, I would say as well. So why is it? Imagine that you are trying, now I'm going to compare software, hardware aspect of a simple operation. Imagine that the operation is to execute a simple logical function and you have 2 bits, 2 inputs, x and y, and when they are 0, 0, 0, 1, 1, 0, the output is 0. It's the function end. And only when both inputs are 1, the output is 1. It's function end, as usual, logical function. Very simple one. A simple logic gate will do it. Now, how to do it in the software? How the processor will do it? It will read the code of operation from the program. Now, stop sharing. It's better to discuss with hand waving. Right? So what the processor does, it reads from the memory, grabs it, code of operation. And the code of operation is do the AND operation. And starts doing an operation. The next is it takes the first operand from where? From memory. Extends its arm, so basically it sends a signal through the bus and grabs, and through the bus delivers into itself this first operand. Then it extends its arm by multiple clock cycles through the bus, grabs another operand from memory, the second one, and through many clock cycles takes it into the CPU. Then it performs the operation inside, which is a very quick one, just one clock cycle perhaps is needed, something like this, very fast. But then it needs to put the result back into the memory. So multiple clock cycles, it puts it there and says, okay, I'm done. I can do the next operation. You see, my explanation was lengthy because I had to do this reach, fetch, do something inside, and then put it back. So this fetch execute style of operation is a long story, multiple clock cycles are required, so it's not fast, obviously. It's not that if the processor is running at 3 gigahertz, it's not that 1/3 of a nanosecond will be required to perform this operation. Multiple clock cycles are required to reach for the data and fetch it back and so on. So the real operation is not computed in those gigahertz. It will be a couple of couple of hundreds of megahertz fast. So in software, such a simple operation is not a good idea. Now, how does it work not in software, but in hardware? So if you want to build a hardware device which does it, it will be just a logic cell. Draw it. 3 inputs, 1 output. Inside you have AND operation. Right? It will be 4 transistors for not AND and 2 transistors for the inverted output. 6 transistors you need. The propagation delay in 90 nanometer technology, which is not new at all, so it's quite slow as well. It will be probably around 20 picoseconds. It's 50 times faster than what you expect at 1 gigahertz. Right? So it's crazily fast. How much energy? You don't need to use the bus. It's just switching one input to the other input and the output, 1 bits everywhere. So instead of switching 64-bit buses every time. So it's very, very efficient. So hardware is hugely more efficient. Energy, so almost no energy in hardware implementation. Huge amounts of energy in the process. Processors are rubbish in computation. So what they are needed for? They need for flexibility and features. That's what we need. So back to here. So these implementations, software and hardware, provide different, absolutely different metrics, different features. Software is hugely flexible. You change the program, it becomes completely different function. Huge amounts of features are possible there, but it's quite slow, energy hungry, not much you can do on the battery and so on. Hardware is extremely efficient in terms of energy, power, and so on. But it is not good with features and flexibility. Right. So in the class today we have a software specialist doing embedded systems course and hardware specialists, microelectronics. You should appreciate both points. Example of DSP as provided in the book by Gupta. It's somewhere in my reading list. Probably not very important. DSP, digital signal processor. It's a special purpose processor which also has interfaces and features to support purely embedded applications in signal processing. It has the code, of course. It's a program. Program is just normal software, right? Just normal, almost just. It's not really normal because it uses special purpose instructions which only exist in DSP. So those instructions are controlling specific features of DSP. DSP code, there are processor cores, so it's a processor, of course. There are specific architecture, specific shapes. So they're designed to stream the data. You have one bus coming in on one side, the other escaping through the other side, and the processor can do operations on the stream of data passing through this chain of buses, instead of using a single bus like a processor for general purpose computation. It has memory like any processor, of course, but this memory is quite close to the processor, and the idea is to maximize the performance, not in terms of throughput, but in terms of latency as well. In general purpose processors, usually it's throughput which is maximized. Therefore, we are using all sorts of caches there. And so there are application-specific gates there and circuits, those which perform specific to DSP operations. And DSP frequently does the conversions between the domains, and frequency domain means Fourier transform, and you need for this accumulate and multiply operations. So this is usually done on a special sets of hardware. Also, DSP processors often employ analog input-output, so the inputs and outputs could be either digital or analog, actually, so it can use it as an analog component, a replacement for an analog component. So have a look at those examples just to get the overall idea, if you wish. DSP is a keyword. Metrics. What are metrics? Design metrics. Time to market. Going to market. So design metrics involve physical and economics metrics. Physical metrics like weight, color, and energy. You're probably familiar. You're engineers. You're familiar with those. Economics metrics. They're quite important because whatever we do, it's the purpose of that is to eventually sell the product. So I just decided to drop here a few economics metrics. Unit cost. It's the fabrication cost of a single copy of the system, excluding the NRE cost. It's defined later. So a single thing should cost something. It's a unit cost. NRE, it's non-recurring engineering cost. It's a one-time monetary investment or cost of designing the system. So now we'll have learned that it's not just the cheapness of a single device which matters, but also how much we spent in advance in order to develop this. And eventually you may want to add the two things together somehow. The total cost, right? So it's where we add things together. It's non-recurring engineering cost, the previous one, plus unit cost multiplied by number of units. So the total of cost in the production. So you're producing a lot of components or a lot of devices, and eventually it costs you something. It's a combination of the single investment in the beginning plus whatever is needed to produce a single device. Per product cost, it's non-recurring cost divided by the number of units plus units. But basically, it's the total cost divided by the number of units. You can see that. So this is per product cost. It's the foundation for the cost or the price for the device. On top of that, of course, you need to add the profit. But the price cannot go below that. Now, some other metrics are time to prototype, time to market. They are timing related. So time to develop a working version of a device, time to prototype. Time to market, time to develop a system to the point where it can be released and sold to customers. Well, time to prototype is shorter than the second one, and the second one is extremely important, will be shown in the next slide. There are drawings there, the graphs there. You'll see that time to market is extremely important because if you're late, then you are not selling, you're not gaining, but the lifetime of the product is limited because at some point will be replaced by another product in the market, and eventually if you arrive there late, then you will not be able to produce enough profit. There are some other metrics such as flexibility. It's the ability to change the functionality of the system without incurring heavy non-recurring engineering costs. It's something to do with software, hardware. Software provides features and flexibility, right? Flexibility. So you see it every time when you buy a new mobile phone. At the beginning, it's quite buggy, and then they release updates to the firmware, and eventually it starts working well. So it's flexibility. What it does, it allows us to cheat and reduce time to market and sell the product which contains bugs. And then by exploiting the feature flexibility, you can fix the bugs, and the customer will be happy in the end. And I'm not focusing on physical metrics, I mentioned them. So here's the explanation of the importance of time to market. Two products are shown here. That's the first product, that's the second product, and the second product was delayed by some time D. Right? This is the peak revenue, so sales go up, and at some point it's the end of the roughly twice the time to the peak from the beginning of the life of the product. It's when the product is substituted by a different one, so it makes no sense to produce after that. And if you delay the entry into the market, then your revenue will be rising, still not sharply, but roughly the same rate. And as a result, this area under the graph, this triangle, becomes smaller than this one. And by how much it's smaller, you can calculate this. It's not a linear dependence, it's non-linear. So longer this delay, smaller the area under the graph, and the losses are quite bad there. So this is to the importance of reducing time to market. For this, we need to reduce time to prototype. This may result in higher non-recurring engineering costs. Probably it may increase even the unit cost, which comes from here. Right? Because when you're designing a device, you see that 3 products of a similar nature, but developed differently. Number of units, volume. So if the number is 0, then this is the non-recurring engineering cost. Why is it? Because total cost, it's the non-recurring unit cost multiplied by number of units. Number of units is 0, therefore we have only non-recurring engineering cost. So the first product, this one, very small non-recurring engineering cost. This product is kind of medium, and this one is high non-recurring engineering cost. By investing more into this non-recurring engineering cost, it's possible to make the product very cheap, very efficient, and you see, adding more and more units, the cost stays almost the same, increases slightly. It means that the product is very cheap itself, but very well designed. This one is designed quite badly, so each unit is very expensive. You see this line goes up quite quickly, but we didn't spend much in the beginning. And at some point, this is the equilibrium point. The equilibrium point is when, for this particular number of units in the volume of production, we have the same result in terms of cost, in terms of whether to invest more into the non-recurring engineering cost or just start producing with bad hardware, kind of not efficient software. Sometimes. Now, which of these products is better at the equilibrium point? I would say probably this bad product at this point is better. Why? Because very little investment at the beginning means that you are not spending much time on this. As a result of this, your time to prototype becomes shorter, time to market becomes shorter, and you enter the market earlier. So sometimes it makes sense to cut down on the quality of development, and instead of that, go for higher cost of a unit, and then you get your money. However, long term, if the production is huge, then it's quite clear that nothing beats a well-developed prototype. So these are things to consider. It's not really a detailed theory in my words. It is just things to consider. All right, so with this, I would like to finish our conversation because it's 12 o'clock. We need to proceed now to the staff student committee, and I'll see you tomorrow for any further chat. Do you have any urgent questions now?
So Alex, this is Raghu. Hello. Hello.
Hello.
You can hear me, right?
Yes, of course.
Yep. So this platform is based on Linux or any real-time operating systems, or like what kind of operating systems will be used for this platform?
We are not going to use the operating system. That's the beauty of this. We are going to develop our own scheduler at a low level.
Okay.
Well, there are some libraries, and you can compile things and link to the libraries, upload to the board, and starts working. And the idea will be to create a so-called time-triggered cooperative scheduler, which is a new concept for you because it's cooperative, first of all. Second, it's real time. It uses all sorts of interrupts and so on inside. And also it is an illustration how on a single processor it's possible to execute independently many things. So it's a multi-task system. You'll enjoy it. Please feel free to have a look in the description of the coursework. There is a description of that, so
sure.
You'll have the details. It will happen in 2 weeks from now, so you don't need to rush. Thank you. Right, if there are no any further questions, then let's leave it until tomorrow. I need to be at a different meeting now. Thank you. Goodbye.